Hello guys, today we'll be reacting to
So before we can test this, let's talk about what a neutron star actually is.
To a drop of neutrons.
So you have normal stars like our sun,
video.
and our sun has a lot of mass. And when you have a lot of mass has gravity, and it wants to compress together, and it wants to attract each other and compress tighter and tighter together. But the reason our sun doesn't just collapse in on itself is because there's another force that's pushing it apart. And that force is due to the explosion that's constantly happening in the sun due to nuclear fusion. So hydrogen is constantly forming into helium and it's exploding the sun. So this exploding force is pushing it out and gravity is pushing it in more and more together. But what can happen sometimes is if there's enough mass, then the mass will keep collapsing in on itself in the star and it'll collapse more and more and more and more until actual electrons are becoming so close together that they become as close together as they can possibly get, and the only thing that's stopping them from overlapping each other is the Pauli exclusion principle. And the Pauli exclusion principle says that you can't have two electrons in the same place at the same time in the same state. But what happens if you try to force them more and more together is the only thing that's holding them apart is due to the Pauli exclusion principle. But it doesn't stop there. If you have too much mass, the mass still wants to attract each other, and not even the Pauli exclusion principle can keep the electrons from getting closer together. So as it keeps compressing stronger and stronger together, the electrons and the protons get so close together that you have electron capture, and it turns a proton and electron into a neutron. And you end up with a pure neutron soup.
A neutron star is formed 100 trillion times
so
more dense than the sun.
Have these protons and electrons, but you have just pure neutrons with no electric charge that can come very close together. So today I want to show you what would happen if you had just a very tiny drop of a neutron star and brought it on Earth. So I have here a magic cube, and what's cool about this cube is we can increase the density up to the density of a neutron star and see what happens. So to start off, let me show you what it looks like. So I have a cube here just at normal Earth density. Put it on there.
Density.
It weighs around only 5 grams.
5,000
now I'm
grams.
going to do my magic touch on this cube. So now it's getting really heavy for the size of it.
Little squares.
Now you can see how heavy it is. Put it in there.
50,000 kilograms.
Instead of 5. Okay, now let's increase the density even more. And go. Whoa. Holy cow. Oh, broke my thing.
So that's what
to me is basically freedom. It's a giant open universe where you can do.
Guys, so that's what happens when a neutron star becomes too heavy.
So you can see it's extremely heavy now. For the size of it, barely pick it up.
Okay, so right now it's 500.
Look at that.
It's really heavy.
Ow. So I would say this weighs around 1 pound now. You can see how heavy it is here. Ow.
So now this weighs 1
I'm
pound.
increasing the density. I can't even hold it anymore. Oh, it went through the table. Okay, so we're going to need a stronger base, but let's just go ahead and turn it all the way up to neutron star and see what happens. 3, 2, 1. Whoa, it just shot through the Earth. So right now it's basically vaporizing the mantle in front of it and leaving a trail of hot plasma behind it. In a while, as it falls, it'll eventually just become lodged in the Earth's core. So let's try this again with a holder that will actually stop it from falling through the table and through the Earth. Okay, now let's redo this experiment with a magic stand that can support the weight of the 100 billion kilograms in that tiny little centimeter cube there. Now because this is so dense, it has its own gravity force that I can feel. And what this feels like to me is that when I start to walk closer to it, it kind of feels like I'm starting to walk down a steep downhill because the gravity is pulling me towards the neutron star instead of straight down towards the Earth. So I kind of feel like I'm walking down a hill. So even just sitting next to it on a table, it's like gravity is pointing that way towards the drop of the neutron star instead of straight down towards the Earth.
So it's really hard.
Okay, now because gravity is proportional to the square of distance,
Going that way.
it becomes increasingly hard to pull away from the neutron star drop the closer you get to it.
Pull away from the
So if you get closer than a critical distance, then you won't be able to get away from it, ever. So that means that if I want to touch this neutron star drop, I'm going to need another plan. And that plan has to do with water. Okay, so I managed to get some water around this. And if I didn't have this box around it, it would look like this. It would be a complete sphere around it with the drop at the very center, because gravity is now pulling it all towards the center. Now normally the point of no return with a drop this size of a neutron star is around 8 inches. Around 8 inches away, your arm would become too heavy to ever pull back, and then it would just get sucked in and probably get ripped off, and it would pull your whole body in and you'd compress down into the neutron star.
Your arm will get ripped off because of the gravitational
force
of the neutron.
So let's see if this orange gets sucked in.
This is what's good. Well,
it just floats. So at this range, it's hundreds of times of Earth's gravity, but it's floating on top here. So that means that buoyancy has nothing to do with the strength of gravity. And the reason it works like this is because the neutron star drop is pulling on the water just as much as it's pulling on the orange. But it pulls on the water a little more because the water's a little more dense. So the orange still floats on top of the water. So this means on different planets, whether it had stronger or weaker gravity than Earth, both would still be able to float just fine. They'd have the same buoyancy as on Earth, because buoyancy is independent of the gravitational factor. So that means my hand should be okay because my hand is less dense than water. So my hand will never get pulled towards the neutron star stronger than water. So as long as I keep it in water, I should be able to get as close to it as I can. But what happens when I get close to it is it's like there's this impenetrable layer I can't get past because my fingers are less dense than water. Basically, I can't penetrate this layer of water because the neutron star is pulling down on the water, no matter what, harder than it's pulling down on my finger. And so no matter what, I can't get through the layer of water around the ball. So even in this situation, even when you have water around it, you're protected from the gravity, but that means that you're going to end up with a very small layer that you can't penetrate with your finger as long as you're less dense than water. Now, if you put some alcohol in this water and you actually became...
When we saw the orb there, and the thing, if there wasn't a container, it's happening with the same because a lot of the water is still in the container. So if it was in the middle, it'll form a big ice cube that you can't put water in it, but you can because it's only forming a circle where it is right now.
More dense than the water, then it would suck your finger in and you wouldn't be able to pull it off. So no matter what, even in this situation, you wouldn't be able to touch a neutron star. You could get very close if you surrounded it with water, but you could never actually touch it. Hey everybody, thanks for watching. The ideas for this video and a lot of the information from it came from the book from Randall Munroe, What If, that I've mentioned before, one of my favorite books. Now, in case you couldn't tell, this video...
So, thanks guys for watching. I will see you in my next video. And bye guys.